So let us start the lecture. We are discussing properties of step function. Okay. So next term is the another useful property of our step functions, and the statement is theorem that phi and b are sequence of step functions, that phi and be a sequence of step functions if a is subset of x, such that this phi it increases to the characteristic function of a, then a is measurable. And the limit of integral of phi, limit of integral of phi n is equal to outer measure of E. Is equal to outer measure of E. So this chi, it's not a step function, it's a simple function, but measure of A may not be finite in general. तो हमने एक रिजल्ट किया ना, if phi n increases to the step function phi, then limit of the integral of phi n will be equal to the integral of the limit function phi, if phi is a step function. तो यहाँ पर chi a step function नहीं है, it's a simple function but not a step function, so we cannot apply that result. अगर ये स्टेप फंक्शन होती तब ये बहुत आसान था, आप डायरेक्टली लिख सकते लिमिट ऑफ इंटीग्रल ऑफ phi n is equal to integral of chi, and integral of chi is equal to the outer measure of E. But this is not a step function here, so we cannot apply that result. Proof. The measurability of A, it's easily follows because phi n is a sequence of measurable functions, so therefore chi A is measurable, since chi A is a measurable function. This is a measurable function, therefore A is measurable, therefore A is measurable. This phi n increases to chi almost everywhere. Okay, this is almost everywhere limit here. Now, as in the previous theorem, we can assume that this phi n of x increases to chi a of x for all x in x. We can assume this as in the previous theorem. We can replace this step function by psi n, which is equal to chi a, then its product with the characteristic function of a set where this convergence hold, say B, where B is a set such that this phi of A n, it increases to chi A, okay, or limit of phi is equal to chi, you can see. So we can see this step function. So you can say step function is it's equal to, because if x is in B, it's equal to chi A, okay, if x in B, because for x in B, chi B of x equal to 1. So if x in B, psi n of x is equal to chi A of x, and B complement is a null set because phi n increases to chi almost everywhere. B is a set of points where this convergence hold. So that means measure of B complement is 0. So and they are equal. They are equal on B, and on B complement psi n is equal to 0. Psi n is equal to 0. So that means psi n is equal to chi A almost everywhere, and psi n it also increases to chi A for each x. You can verify this thing. This psi n, it increases to chi A for all x, So we can replace this psi n by chi A in case this convergence does not hold for all x in x. या ऑलरेडी हमने किया है एक्सप्लेन ना, एक थ्योरम है वहाँ पर हमने पूरी डिटेल में लिख दिया है. हम स्टेप फंक्शन इसको रिप्लेस करेगी with another sequence of step functions. So we can assume this phi n of x increases to chi A of x for all x in x. Now for each n we define a set. For each n we define an. Okay, we define an. For each n, the set an, which is equal to the set of the points x in x, such that phi n of x is positive. Okay, because since phi n is a step function, so measure of an is finite. It's a measurable function also fine. That means a is measurable. It's also measurable with finite measure. Then an is measurable of finite measure. For each set define this. For each n define the set. Okay. Then each an is measurable and measurable of finite measure of finite measure, because phi n is a step function. Phi n is a step function. Okay, this is the reason it's a step function, because phi n is a step function. So they are measurable with finite measure. And we also see that this sequence is monotonic increasing of sets. Also if x is an, then by definition phi n x is positive, which implies phi n plus 1x is also positive, because phi n plus 1x is greater or equal to phi x, as it's increasing sequence. This is also positive. That implies x belongs to an plus 1. So therefore this is true for all n greater or equal to 1. Therefore an is subset of an plus 1. So it's increasing sequence. Now this next, this union. What's the union? Union of an. n runs from 1 to infinity. It's equal to a. तो ये आपके लिए assignment है. Please check this union is equal to a. So therefore, by our notation, therefore this an, it increases to a. An increases to a. and it follows that chi of a n increases to chi a, because we know that since अगर ना वो कैरेक्टरिस्टिक फंक्शन जो आपने किया है सिंस मैं इसको पूरा यहाँ लिख दूंगा सिंस chi of union is equal to sum of the chi's, okay, chi of union means chi of a. Let's write it as chi of a, okay, this thing it's equal to chi of union n runs from 1 to infinity, and this thing it's equal to summation, but these an's they may not be disjoint, they may not disjoint, so how can we apply that theorem? It's we cannot apply it here. Because it is not a disjoint sequence, so this thing, but still we can replace this union by a disjoint union, that can be done, but उससे हमें मिलेगा chi. I want to show that chi of a n will increase to chi of a, so chi of the union a n should be equal to that should be equal to limit, actually limit of chi of a n it's possible disjoint union this chi of disjoint union, it is actually disjoint union bn, let's write here union bn, okay, union bn and runs from 1 to infinity. Where this bn it's equal to an minus 1, okay, a1 is b1, a2 is b2, okay, bn is equal to an set difference minus an minus 1 union up to an minus 1, because since it is an increasing sequence, so union a1 a2 up to an minus 1 it's equal to an minus 1, so don't need to write here this now it's okay, it's now correct. So since chi a which is equal to this, let's write here now, not since let's write here now. Now this chi of a which is equal to chi of the union bn, where bn is they are now disjoint sets, because b1 is equal to a1, b2 is equal to a2 minus a1, b3 is equal to a3 minus a2, so on and so forth. It's a disjoint sequence of measurable sets. Okay, so this is equal to summation n runs from 1 to infinity chi of bn. Now we can write this, and that's equal to limit n approaches to infinity summation k runs from 1 to n chi of bk. chi of bk. Okay, chi of bk. So this a bk, it's equal to summation k runs from 1 to n chi of bk. That result is for disjoint sequence. We cannot apply that result here. That sequence should be a disjoint sequence. So now here I want to convert it into chi of bk. Okay, this is equal to, okay, let's write it like this: limit n approach to infinity. Now this one, it's called chi of union bk, k runs from 1 to n. Okay, this thing is equal to limit n approach to infinity chi of a n. That's it. Because the union bk k runs from 1 to n is equal to union an or union ak k runs from 1 to n, which is equal to an, because n is an increasing sequence. Because union bk k runs from 1 to n is same as the union ak k runs from 1 to n, and that's equal to an. So therefore limit of chi of n is equal to chi of a. Therefore limit chi an is equal to chi a. Also chi of an is less than or equal to chi of an plus 1, because an is subset of an plus 1 for all n greater or equal to 1. So therefore this limit is actually the increasing limit. Therefore this limit, it's therefore chi of an, it increases to chi of a. It increases to chi of a. So it means that we have two sequence of step functions. Also this is a sequence of step function because n is a finite measure. Also this phi n, it's given that this phi n increases to chi a. तो आपके पास दो सीक्वेंसेस है स्टेप फंक्शंस की जो कि एक ही फंक्शन पर कन्वर्ज हो रही है, chi a. नाउ यू कैन अप्लाई द प्रीवियस थ्योरम, जहां पर आपने देखा कि अगर लिमिट एक ही होगा दो स्टेप फंक्शंस का, तो उस केस में लिमिट ऑफ इंटीग्रल ऑफ फर्स्ट स्टेप फंक्शन सीक्वेंस ऑफ स्टेप फंक्शन इज इक्वल टू द लिमिट ऑफ द इंटीग्रल ऑफ सेकंड सीक्वेंस ऑफ स्टेप फंक्शंस. सो बाय प्रीवियस थ्योरम, we obtain the following. We obtain this: limit n approach to infinity integral of phi n is same as limit n approach to infinity integral of chi of an. But the integral of chi of n is equal to the outer measure of n. That's the definition of the integral of step function. It's a step function with only one set a. It's mu star a. But since a n increases to a, therefore mu star of a n increases to mu of a. This is equal to mu of a, mu star of a. As because a n increases to a. So that proves the theorem. That proves the theorem. That proves this theorem completely. Okay, now next theorem, which is very important. So we'll see that every measurable function can be obtained from the sequence of step functions actually. तो ये रिजल्ट आपको समझ आ गया दिस वन. Next theorem. Let f from x to r, f from x to r be a measurable function. This be a measurable function satisfying fx greater or equal to 0 for all x. Then there exists a sequence of step functions. Then there exists a sequence of step functions. There exists a sequence of step functions phi n not a sequence, it's a simple function. Okay, simple functions, simple functions. Okay, phi n such that each simple function is non-negative. Okay, and this increases to function fx for all x in x. So actually this set of the step function, it is the building blocks for the class of non-negative measurable functions, because any measurable functions can be obtained from the step functions, from simple functions. तो अगर आपके if you know all about simple functions, you may know all about the measurable functions, because every measurable functions can be constructed, or you can say the measurable functions or you can say this class of simple functions जो है ना, it's actually dense in the class of measurable functions. Okay, so this result is very important, this one. And its proof is also very important. It's based on the construction, because अब आपके पास क्या, आपके पास सिर्फ measurable function, it may be any function, और वहाँ से आपको simple functions कंस्ट्रक्ट करनी है. सिंपल फंक्शन यू नो विच इज फाइनाइट वैल्यूड, और फिर आपको चेक करना है वो जो सिंपल फंक्शंस है, वो जो सीक्वेंस आपने कंस्ट्रक्ट की है, दैट सीक्वेंस विल कन्वर्ज टू आवर गिवन मेजरेबल फंक्शन. So how do we do that? We define sets. We define sets. So for simple functions we must define sets. Then we must define the characteristic function of those sets. Then we take their linear combinations, and finally we will see that finite linear combinations, they are actually simple functions, and then we check the convergence of that sequence of simple functions. So let's first define sets. For each n we define for each n, so let a and I okay, is equal to set of the points x belongs to x such that I minus 1 2 power minus n less or equal to f of x and less than I times 2 power minus n. This is a and I, where what is this I? For I equal to, for I is equal to 1 2 n 2 power n. तो इस फंक्शन की मदद से आपने आप एक सेट डिफाइन किया. Sequence of sets you have defined a1, a2, a1i, a2i, a3i, so on and so forth. So you have defined these sets. Now we see that these sets, they are disjoint with respect to I. We show that, or we claim that. We claim that these sets A and I intersection A and J with respect to fixed n, okay, A and I AJ is empty for I not equal to J. Okay, so let's check this one. They are disjoint sets. So assume this I is less than J, okay. So suppose I is less than J, because I is not equal to J, so we can assume either I less than J or I greater than J, and assume on contrary that assume on contrary that this intersection A and I intersection A and J is non-empty. So that means we can choose a point in this set, okay. Let's choose the point x. अब आपको डेफिनेशन पर कंसंट्रेट करना. व्हाट्स डेफिनेशन ऑफ ए एन आई एंड व्हाट्स डेफिनेशन ऑफ ए एन जी, तो वो आपको देखना है. सो डेफिनेशन ऑफ ए एन आई क्या है? इट्स एक्स एज एट आई माइनस वन टू पावर माइनस एन लेसर इक्वल टू एफ एक्स लेस देन आई टू पावर माइनस एन. इसी तरह से ए एन जे की डेफिनेशन क्या है? जे माइनस वन टू पावर माइनस एन लेसर इक्वल टू एफ एक्स लेस देन जे टू पावर माइनस एन. So we choose a point in both the sets A and I as well as in A and G. So let's choose that point. So we can choose a point, choose X in the intersection. A and G. Then from this A and I we have I minus 1 2 power minus n lesser equal to fx and less than I times 2 power minus n, and from the second one it's j minus 1 2 power minus n lesser equal to fx less than j 2 power minus n. Now this I is less than j, okay, I is less than j, so I minus since they are integers I less than j, which means that I minus 1 lesser equal to j. So therefore we start with this I minus 1, therefore I minus 1 2 power minus n lesser equal to fx, and fx is strictly less than I into 2 power minus n, and this I it's lesser equal to I is lesser equal to j minus 1 actually, yeah, I is lesser equal to j minus 1. This I is lesser equal to j, I is less than j, which means that I is lesser equal to j minus 1, okay. तो यहाँ ये mistake हुई थी, I is lesser equal to j minus 1. This I is lesser equal to j minus 1, okay, j minus 1 into 2 power minus n. Now what's j minus 1 2 power minus n? It's lesser equal to fx. बस इतना ही मुझे चाहिए. This is. Now from this we conclude that fx is strictly less than fx, which is a contradiction, which implies fx is strictly less than fx. Why it's a contradiction? Fx is strictly less than fx, which is a contradiction. So therefore A and I intersection A and J, they are disjoint for I not equal to J. They are disjoint sets. So this the function f is measurable. Okay, our function f is measurable. Therefore, each a and I is measurable because each a and I is inverse image of set in a semi-closed interval, which is a measurable set. Since f of x is measurable, therefore a and I, which is actually equal to f inverse image of it's here I minus 1 2 power minus n and I 2 power minus n. Therefore this set A and I, which is inverse image of this, it's a Borel set actually, semi-closed interval hai. Semi-closed intervals are Borel sets. So it's a Borel set, and inverse image of Borel set is measurable if the function is measurable. This is measurable, is measurable for all n and I equal to 1, 2 and 2 power n. So these sets are measurable sets. They are actually measurable sets. Now we define as simple function. Now define a phi n, which is equal to summation I runs from 1 to n 2 power n, and 2 power n, then it's here 2 power minus n of I minus 1, I minus 1 into characteristic function of a and I. It's a finite value because it's a finite sum. So then this phi n, it's also measurable because a and i's are measurable. Then phi n is finite valued and measurable. Finite valued and measurable. Therefore a step function, therefore a simple function, therefore a simple function, therefore a simple function, okay, for all n greater or equal to 1. Okay, thus we have a sequence of simple functions, and they are also non-negative. They are also non-negative because it is the finite sum of the step function, and the coefficient of each step function is non-negative. Also, this phi n x, it's greater or equal to 0 for x. Equal to 0 bhi hoga because if this point is outside of these sets a and i's, okay, then it's equal to 0. It is greater or equal to 0 for all x and x. So we have a sequence of non-negative simple functions. Now we will show that this sequence is monotonic increasing, and the limit of this sequence is fx. That will complete the proof of theorem. Now we show that phi n x is less or equal to phi n plus 1x for all x in x. Okay. So if this x is in certain a and I, if it's not in any a and I, if x does not belongs to a and I for all n greater or equal to 1, suppose ये किसी भी a and I में नहीं है, then what's phi n x? Then in that case, what's phi n x? It's a sum, okay, summation I runs from 1 to n into 2 power n, that it's 2 power minus n times I minus 1 characteristic function of a and I evaluated at x. This will be equal to, अगर ये किसी भी a and I में नहीं होगा, उस केस में ये किसके बराबर होगा? 0 के बराबर. So therefore phi n x is less or equal to phi n plus 1x in this case, because phi n x is always greater or equal to 0. Okay, so phi n plus 1, it may be 0 or it may be greater than 0, but this thing is equal to 0, so that means phi n x is less or equal to phi n plus 1x in that case. So next we show that suppose if it is in certain a and I, अगर ये किसी एक a and I में, एक ही a and I में होगा because a and i's are disjoint with respect to I, and here for each phi n this n is fixed, so you are varying only I, and with respect to I, a and I is disjoint. Okay, that you have seen, it's a disjoint sequence. So if it is in exactly one a I, certain a and I, then in